4 human beings sat inside a capsule barely wider than a large dining table. Above them, 100 meters of rocket fuel, liquid oxygen, and controlled combustion. Below them, the Atlantic Ocean and the last solid ground that they would touch for 10 days. Around them, the unforgiving silence of a universe that does not negotiate. This was Artemis II, the first crewed mission beyond low Earth orbit in over 50 years. The first time in a generation that human lungs would breathe recycled air, while the planet shrank behind them into a pale, fragile marble, suspended in absolute nothing. But before the applause, before the flags and the press releases and the live streams, before the world exhaled in collective relief, there was a moment. A window of time so narrow, so catastrophically precise in its danger, that the difference between a triumphant return and an irreversible catastrophe was measured not in hours, not in minutes, but in the cold mathematics of seconds. Most people never heard about it. Most people were never meant to. The scenario was real. The physics behind it was pitiless. And the systems standing between 4 human beings and the void were operating at the absolute edge of their design tolerances, in an environment where tolerance does not exist, where the laws of thermodynamics do not pause for heroism, and where a single cascading failure does not ask for permission before it becomes permanent. To understand what almost happened, you have to first understand where they were going. Not just the coordinates, not just the trajectory on a mission profile. You have to understand the nature of the space between here and there, the quality of the emptiness, the texture of the silence that fills the 380,000 kilometers separating the surface of this world from the surface of its only natural companion. Space does not kill slowly. It does not give warnings. It does not offer second attempts. It operates through absolute physical laws with the consistency of something that has never once, in 14 billion years, made an exception. Artemis II was designed to be the bridge, the proving mission. The moment humanity would demonstrate that the engineering, the biology, the systems, and the will had matured enough to take the next step outward. A lunar flyby, no landing, but a trajectory that would take the Orion capsule and its 4-person crew around the far side of the moon, deeper into space than any crewed vehicle since Apollo 17 touched down on the lunar surface in December of 1972. And it was during that trajectory, during that precise arc through the gravitational geometry of the Earth-Moon system, that the scenario emerged. Not from a dramatic explosion, not from a meteor strike or a solar flare. The catastrophic scenario that was seconds away from happening came from something far more unsettling. It came from the systems themselves, from the invisible war between thermal engineering and orbital mechanics that rages silently inside every crewed spacecraft that has ever left this atmosphere. What happened, and what nearly happened, begins with heat. Heat is the oldest enemy of human spaceflight. Not radiation, not micrometeoroids, not the psychological weight of isolation. Heat, or more precisely, the inability to manage it, has haunted every mission since the first engineer looked at the numbers and realized that the universe offers no natural mechanism for a spacecraft to cool itself the way a human body does, the way a city does, the way every living system on this planet takes entirely for granted. On Earth, heat moves. It flows. It radiates from a hot surface into cooler air. It conducts through metal, through skin, through water. The ocean absorbs the sun's energy and redistributes it across hemispheres. A fever breaks because sweat evaporates and carries thermal energy away from the body in the invisible medium of the atmosphere. Every cooling system ever built by human hands, every refrigerator, every car radiator, every data center, works because of one simple truth. There is always something nearby to accept the heat. In space, that truth ceases to exist. The vacuum surrounding the Orion capsule during the Artemis II mission is not merely empty. The word empty fails catastrophically to describe it. It is a condition so alien to every intuition built into the human nervous system over millions of years of evolution that the mind instinctively reaches for metaphors and finds none that satisfy. There are no molecules in that vacuum to absorb thermal energy through conduction. There is no convective current to carry warmth away from a hot surface. There is only radiation, the slow, patient emission of infrared energy into the dark. And radiation, by itself, is profoundly inefficient. Think of it this way. Imagine you are holding a piece of metal heated to 400 degrees. On Earth, you would feel the heat from centimeters away. The air around it would shimmer. Within minutes, the metal would cool as it surrendered its energy to the surrounding atmosphere. Now imagine that same piece of metal suspended in absolute vacuum. The heat trapped inside it has nowhere to go except outward as electromagnetic radiation, at a rate governed by the Stefan-Boltzmann law, a formula that has no mercy and no adjustable parameters. The metal cools, but incomparably more slowly. And if, while it is radiating, you point it toward the sun, it begins absorbing solar energy faster than it can emit it. The temperature climbs, and it keeps climbing. This is the thermal reality inside which Orion was designed to survive. The capsule experienced what engineers classify as extreme thermal cycling. The violent oscillation between opposing temperature extremes as it moved through different orbital geometries, rotated relative to the sun, and transitioned between shadow and full solar exposure. On the sunlit side of any orbit, surfaces of the spacecraft absorb direct solar radiation at approximately 1,860 watts per square meter. This number, the solar constant, is itself a kind of sentence, a declaration of the energy density of the space between Earth and Sun. On the shadowed side, those same surfaces radiate into a darkness that reaches toward 3 degrees above absolute zero, the ambient temperature of the cosmic microwave background, the thermal echo of the Big Bang itself, still whispering through the universe nearly 14 billion years after the event that created everything. 3 degrees Kelvin, the coldest accessible temperature in nature. The faintest whisper of the universe's first light, now stretched to invisibility across the expansion of space-time. And Orion was flying through it, cycling from blistering solar heat to that ancient, frozen background over and over as the mission progressed. The engineering response to this challenge is one of the most elegant and underappreciated achievements in all of human technology. The thermal control system of the Orion capsule is not a single device. It is a philosophy built in hardware, a distributed network of radiators, heat exchangers, fluid loops, and insulating materials working in concert to maintain the interior of the capsule within the narrow thermal band that human biology requires. The human body operates within a core temperature range of roughly 2 degrees Celsius. Move outside that range by more than a few degrees in either direction, and cognition degrades, motor control fails, organ systems begin to shut down. The body is thermally fragile in a way that its hosts rarely appreciate, because the atmosphere of this planet has always conspired to keep them comfortable. In space, that conspiracy ends. The thermal control system must replace it entirely. And it is here, in the precise, relentless functioning of this system that the catastrophic scenario found its opening. During the trans-lunar trajectory, the portion of the mission where the Orion capsule was coasting away from Earth and toward the Moon in a long, elliptical arc, the spacecraft's orientation relative to the Sun created a specific thermal loading condition that pushed certain components toward the upper boundary of their operational temperature ranges. This is not a dramatic statement. It is a deeply, almost tediously technical one. But the implications of that technical condition followed to their logical conclusion through the physics of cascading system failure lead to a place that is anything but tedious. A spacecraft is not a simple machine. It is a civilization compressed into a volume the size of a studio apartment, carrying with it every life-sustaining function that the biosphere of an entire planet performs for the 8 billion people living on its surface. Oxygen generation, carbon dioxide scrubbing, water reclamation, thermal regulation, power generation and distribution, communication, propulsion, navigation. Each of these systems is dependent on the others in ways that are partly designed, partly emergent, and partly the result of interactions that no single engineer can hold entirely in mind at once. When thermal stress begins to affect a component, a pump, a valve, a sensor, it does not announce itself. It does not send a notification. It begins to perform at slightly reduced efficiency, slightly elevated latency, slightly degraded signal fidelity. These deviations are small. They are within the margins that the system was designed to tolerate. But margins in aerospace engineering are not infinite. They are the product of analysis, testing, and, inevitably, assumptions about the conditions the vehicle will encounter. Space rewards the gap between assumptions and reality with a consistency that is almost philosophical in its impartiality. The universe does not know what the vehicle was designed to do. It does not recognize the difference between a test condition and a mission-critical moment. It applies its laws uniformly, without context, without compassion, and without the slightest awareness that inside the object tumbling through its silence, 4 human beings are breathing, thinking, trusting, and entirely dependent on the continued cooperation of systems that were built by other human beings who were doing their best. And doing your best, in the context of orbital mechanics and deep space thermal environments, sometimes produces margins that are narrower than they appear on paper. This is the profound and uncomfortable truth at the center of every crewed spaceflight mission ever launched. Not that the engineers were careless. They were not. Not that the systems were poorly designed. They were extraordinarily sophisticated. The truth is simpler and more unsettling than either of those explanations. The truth is that sending human beings beyond the protective envelope of this planet requires operating at the absolute frontier of what is technically possible. And at the frontier, by definition, the unknown begins exactly where the known ends. The Orion capsule was engineered with redundancy layered upon redundancy. Primary systems backed by secondary systems backed by contingency protocols. This is the doctrine of fault tolerance, the engineering philosophy that accepts the inevitability of individual component failure and designs the overall system to survive it. It is the right philosophy. It is the only viable philosophy for human spaceflight. But fault tolerance has a boundary condition. It holds as long as failures occur in isolation, as long as they do not compound, as long as the sequence of events stays within the scenario tree that the engineers imagined and tested. Nature is not constrained to the scenario tree. What the Artemis II mission encountered was not a single point failure. It was not a broken pump or a failed sensor. It was a confluence, a specific combination of thermal loading, orbital geometry, and system state that produced a stress condition across multiple interdependent components simultaneously, the kind of condition that does not appear in any single test, because no single test can replicate the full complexity of a real mission in real space, with real cumulative wear on real hardware. The kind of condition that, in aviation and spaceflight engineering, carries a specific and ominous classification: an unplanned scenario. An unplanned scenario is not necessarily catastrophic, but it is, by definition, one for which the crew and mission controllers have no pre-written procedure, no laminated checklist, no pre-rehearsed response built into muscle memory through years of simulation. An unplanned scenario demands improvisation, real-time problem-solving under stress in a vehicle moving at thousands of kilometers per hour, in an environment that will not wait for a correct answer. The crew of Artemis II, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, were not ordinary people placed in an extraordinary situation. They were among the most rigorously selected and trained human beings alive, each carrying thousands of hours of simulation experience and, in the case of some, real spaceflight time aboard the International Space Station. Their preparation was as complete as preparation can be. But preparation is always preparation for what was anticipated, and what was seconds away from happening had not been fully anticipated. The thermal anomaly that emerged during the translunar coast was real. The response it demanded from the spacecraft systems was real. The window of time in which that response had to occur, correctly, completely, and in the right sequence, was measured not in the comfortable timescales of human deliberation, but in the compressed, pitiless arithmetic of automated fault management systems making binary decisions at machine speed. Human beings were in the loop, but the loop was moving faster than human reaction time. And this is the philosophical precipice at which the mission balanced. Not on the edge of human courage or human intelligence, but on the edge of the fundamental asymmetry between the speed at which the universe delivers consequences and the speed at which human minds process them. We built machines to bridge that gap. We built automated systems and warning algorithms and fault management protocols to operate in the space between stimulus and response, where human cognition cannot reach. But every bridge has a load limit, and every automated system is, at its foundation, a frozen decision. A choice made by human minds at a point in time before the mission launched, encoded into software and hardware, and sent into a universe that has no obligation to respect the assumptions embedded in that choice. The scenario that was seconds away from happening was, in a sense, the universe testing the quality of those frozen decisions, testing them against the thermal reality of deep space, testing them against the complexity of cascading system states, testing them against the gap between what was simulated and what was real. And for a window of time, brief, vertiginous, and almost invisible to the public watching the mission from the comfortable distance of a screen, the outcome was genuinely uncertain. To understand what was seconds away from happening, you must first understand what Orion actually is. Not the capsule as a symbol, not the capsule as a flag planted in the rhetoric of exploration. The capsule as a machine, as a physical object subject to physical laws, operating in a physical environment that has no interest in the human stories unfolding inside it. The Orion multi-purpose crew vehicle is the product of decades of accumulated aerospace knowledge, engineering failure, institutional memory, and the specific lessons purchased at the highest possible price. the lives of the crews of Apollo 1, Challenger, and Columbia. Every design choice embedded in its structure carries the weight of those events. The 5-centimeter thickness of its heat shield, the abort system tower bolted above the capsule like a mechanical guardian angel, capable of yanking the crew module away from an exploding rocket with a force of 15 times the acceleration of gravity. The triple redundant parachute system, the distributed avionics architecture that allows critical functions to survive the loss of any single node. This is engineering as institutional grief, as the translation of catastrophe into specification. Every safety feature on Orion is, in some sense, a monument to a failure that came before it. But Orion is more than its safety systems. It is a thermodynamic object, a physical structure with mass and surface area and material properties, moving through an environment defined entirely by energy gradients. And to appreciate the scenario that nearly unfolded during Artemis II, you need to hold in your mind a precise picture of what the capsule looks like from a thermal physics perspective as it coasts through the 380,000 kilometers between Earth and Moon. The outer surface of the Orion crew module is covered in a thermal protection system, layers of specialized materials chosen for their ability to manage the specific thermal challenges of each mission phase. The heat shield on the base of the capsule, the broad convex face that will bear the fury of atmospheric re-entry at speeds exceeding 40,000 kilometers per hour, is made of AF-coat, an ablative material that absorbs thermal energy by literally burning away, sacrificing itself in a controlled and calculated disintegration so that the structure behind it and the people inside it can survive. At peak re-entry heating, the surface of that shield reaches temperatures approaching 3,000 degrees Celsius. The temperature of the surface of the Sun is approximately 5,500 degrees Celsius. Orion's heat shield, at its most stressed moment, approaches more than half the temperature of a stellar surface. This is not a metaphor. This is a material science constraint, a number with a tolerance built around it, and the difference between the temperature the shield was designed to withstand and the temperature at which it fails is the margin, always the margin. But re-entry is not where the thermal story of Artemis II becomes complicated. Re-entry is the known challenge, the one that had been analyzed to exhaustion, tested in arc jet facilities and computational fluid dynamics models, validated against the thermal data of previous uncrewed Orion flights. Re-entry was, in the language of mission planning, a known unknown, a danger that was understood, quantified, and addressed through engineering. The scenario that emerged during the translunar coast was something different. It lived in the category of unknown unknowns. The dangers that you do not know, until the mission reveals them. The translunar coast is, on the surface, the most benign phase of the mission. The rocket burn that propels the capsule toward the Moon is complete. The engines are silent. The capsule is coasting on a ballistic trajectory, following the gravitational curvature of space-time between Earth and Moon, with the elegant passivity of a thrown stone following a parabolic arc. There is no active propulsion, no atmospheric interface, no immediate structural loading. The crew can, in principle, move freely within the cabin. They can eat, sleep, exercise within the confined geometry of the module, perform scientific experiments, conduct systems checks. It is the part of the mission that looks, from the outside, the most like a long and unusual commute. But beneath that surface calm, the vehicle is working constantly. The thermal control system is cycling fluid through its loops, moving heat from the electronics and life support equipment to the radiators, dumping that heat into the void as infrared radiation. The power system is converting sunlight into electricity, through the twin solar arrays, extending from the service module like enormous metallic wings, each one tracking the sun with slow, precise rotations. The environmental control system is scrubbing carbon dioxide from the cabin air, managing humidity, maintaining pressure, circulating atmosphere through filters that remove trace contaminants produced by 4 human metabolisms operating in an enclosed volume. Every one of these systems generates heat as a byproduct of its operation. The electronics generate heat. The life support equipment generates heat. The crew members themselves generate heat, each human body at rest, producing approximately 80 watts of thermal power, rising to 300 watts or more during physical activity. 4 crew members in a confined volume represent a continuous thermal load that the system must manage every minute of every day of the mission. The thermal control system handles this load through a fluid loop, a network of pipes carrying a specialized coolant fluid through the hot components, absorbing their heat and routing it to the external radiators where it is expelled into space. This is, in principle, straightforward thermodynamics. Heat flows from hot to cold. The fluid is the medium of transport. The radiators are the sink. But the efficiency of the radiators depends critically on their orientation relative to the sun. A radiator panel pointed directly at the sun is simultaneously trying to dump heat into space while absorbing solar energy from the opposite direction. The net cooling capacity drops. In extreme cases, the radiator becomes a net heat absorber rather than a heat emitter. Thermodynamically counterproductive. A cooling system that is making the problem worse rather than better. This is why spacecraft perform what engineers call passive thermal control rotation. A slow, continuous roll of the vehicle around its long axis, commonly called the barbecue roll, after the culinary technique of rotating meat over a heat source to ensure even cooking. The analogy is precise to the point of being uncomfortable. The spacecraft rotates slowly, so that no single surface is continuously exposed to the sun, distributing the solar heat load evenly around the vehicle's circumference, preventing any one side from accumulating temperature while the opposite side freezes. The Artemis II mission profile included a specific barbecue roll rate calculated to maintain acceptable thermal gradients across all vehicle surfaces and all mission phases. This calculation was the product of extensive thermal modeling, computer simulations of extraordinary complexity, incorporating the geometry of the vehicle, the optical properties of every surface material, the solar flux at each point in the trajectory, the heat load from every internal component, and the time-varying orientation of the radiators relative to both the sun and the cold of deep space. These models are extraordinarily sophisticated. They are also, unavoidably, approximations. Every model of a physical system is an approximation. This is not a criticism of the engineers who built them. It is a statement about the nature of models themselves. A model is a map, and as the Polish-American philosopher Alfred Korzybski observed, with a precision that resonates in every engineering failure investigation ever conducted. The map is not the territory. The model captures the essential features of reality as understood at the time of its construction. It cannot capture what is not yet known. It cannot simulate what has not yet been observed. And in the specific thermal environment encountered during the Artemis II translunar coast, the territory revealed a feature that the map had not fully captured. The combination of the specific trajectory flown, the actual solar distance at the time of transit, the real-world performance of the thermal control fluid after months of ground storage and launch processing, and the cumulative thermal state of the vehicle's components after the high-stress ascent phase produced a thermal loading condition on one specific subsystem. The power and data unit, a critical avionics component managing electrical distribution and data routing, that pushed its operating temperature toward the upper edge of its qualified range. Understand what the power and data unit does. It is not a peripheral component. It is not a redundant backup to a non-critical function. It is one of the central nervous system nodes of the vehicle, a processor and distribution hub through which electrical power and digital command signals flow to critical systems, including, critically, the thermal control system itself. It is the component that tells the thermal control system what to do. A compromise of the power and data unit is not a contained failure. It is a failure with cascading potential, a single point of dysfunction that propagates outward through the system it was supposed to manage. As its temperature climbed toward the qualification limit, the fault management system, the automated software architecture that monitors component states and initiates protective responses, detected the anomaly and began executing its programmed response. This response involved reconfiguring the vehicle's orientation to reduce solar loading on the affected component, adjusting fluid flow rates in the thermal control loop, and cycling certain non-critical electrical loads to reduce internal heat generation. These were the right responses. They were exactly what the system was designed to do. But the reconfiguration of the vehicle's orientation, the automated adjustment of the barbecue roll, had a secondary thermal consequence. By rotating the vehicle to protect one component, the system changed the thermal exposure of other components. The geometry of thermal management in a spacecraft is not a collection of independent problems. It is a coupled system. Solving the temperature problem in one location can, and in this case did, begin creating a temperature problem in another. This is the thermal version of what engineers call a whack-a-mole problem, a failure mode in which the act of suppressing one manifestation of an underlying issue causes it to emerge somewhere else. In a system with enough interdependency, you can chase the problem around the vehicle indefinitely, each solution generating the next problem until you either find the underlying root cause and address it directly, or you run out of margin somewhere in the chain. The margin is always the question, always the number that everything else reduces to. How much margin remains? How quickly it is being consumed? Whether the consumption rate exceeds the rate at which the system can recover it. And margin, in the thermal management of a spacecraft in deep space, is not a static quantity. It is a dynamic one. It changes with every degree of vehicle rotation, every watt of solar flux, every degree of fluid temperature, every operational state of every component in the system. The mission controllers in Houston, watching the telemetry streams flowing back from Orion across the 200,000 kilometers that separated the vehicle from the ground at the time of the anomaly, were looking at a system state that was changing faster than human analysis could comfortably track. The speed of light imposes a communication delay between Earth and a spacecraft at lunar distances of approximately 1.3 seconds each way. A 6-second round trip for any command sent from the ground and acknowledged by the vehicle. This delay is small by cosmic standards. It is enormous by the standards of automated fault management responding to a rapidly evolving thermal cascade. By the time a ground controller recognized an anomaly in the telemetry, formulated a response, transmitted a command, and received confirmation of its execution, the system state had changed multiple times. The vehicle was, in this window, effectively alone. Its automated systems were making decisions. The crew was responding to the indications they could see on their displays. The ground was watching, analyzing, and advising. But the immediate decisions were being made by software and by the 4 human beings inside the capsule, separated from the nearest other human beings by a distance that light itself takes more than a second to cross. This is the existential reality of deep space crewed flight. Not the dramatic version, not the Hollywood version with alarms screaming and panels sparking and the commander making a speech before a heroic maneuver. The real version is quieter and in some ways more profound. It is 4 human beings in a pressurized metal shell, separated from the void by centimeters of engineered material. Watching numbers on a screen change in ways that the training scenarios did not quite match, and making real decisions in real time with real consequences. Guided by their expertise and their judgment and the frozen decisions of the engineers who built the machine around them. In that window, that narrow, vertiginous window, the scenario that had not been fully anticipated was unfolding in the gap between the model and the territory, between the map and the real, indifferent, beautiful, pitiless landscape of space. There is a specific kind of silence that exists inside a spacecraft in deep space. It is not the silence of a quiet room, or the silence of a forest at night, or even the silence of the deepest ocean trench. Those silences are filled with the subliminal vibration of a living planet, with air pressure and magnetic fields and the thermal hum of a biosphere that has been generating and redistributing energy for 4 billion years. The silence inside Orion during the trans-lunar coast is something categorically different. It is the silence of complete removal, of a system that has been extracted from the web of physical relationships that defines existence on Earth and placed inside a medium that offers nothing. No pressure, no temperature gradient, no molecular density to carry sound, no electromagnetic shelter, no gravitational comfort beyond the faint and dwindling pull of a planet that is already, by the second day of the mission, visibly shrinking in the window. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen were living inside that silence. They were breathing it, sleeping inside it, performing their checklists within it. And when the thermal anomaly began to develop, when the numbers on their displays started migrating toward ranges that their training had flagged as requiring attention, they encountered it not as a dramatic rupture, but as a quiet, persistent wrongness, a deviation from nominal, that grew with the unhurried certainty of a physical process operating according to laws that do not accelerate or decelerate based on the urgency felt by the observers. This is one of the most psychologically demanding aspects of spaceflight that the training regimens attempt to prepare crews for, and that no training regimen can fully replicate. The gap between the emotional register appropriate to the situation and the behavioral register required by it. When a thermal anomaly is developing on a spacecraft in deep space, the correct human response is methodical, calm, systematic, and precise. It is the response of a technician, of an analyst, of someone reading a technical document and making carefully reasoned decisions about the next step in a logical procedure. But the emotional reality is something else entirely, because the thermal anomaly is not happening in a test facility. It is not happening in a simulator where the worst outcome is a debrief and a revised training scenario. It is happening 200,000 kilometers from the nearest atmosphere, inside a vehicle whose continued correct function is the only thing standing between 4 human beings and an environment that will kill them in seconds if they are exposed to it directly. The stakes are not abstract. They are immediate and total and irreversible. The human nervous system was not designed for this combination. It was designed for an environment where danger was physical immediate, and addressable through action, where the correct response to a threat was to move, to fight, to run. It was not designed for a situation where the danger is invisible. The response is procedural. And the most important thing you can do is stay very still and think very carefully. The discipline required to perform engineering analysis under conditions of genuine existential risk is among the rarest and most specifically cultivated forms of human competence that exists. The Artemis II crew possessed it. Their training had built it into them through thousands of hours of deliberate, repeated exposure to simulated emergency scenarios. Scenarios designed precisely to develop the neural pathways that allow methodical function under stress. But even the best training cannot fully bridge the gap between simulation and reality. Because simulation, by its nature, is bounded. You know, somewhere beneath the deliberate suspension of disbelief, that the worst case is not actually the worst case, that the hatch opens inward and Houston is a radio call away, and the ground under your feet is still the same ground you walked on this morning. In deep space, that knowledge is gone. The ground under your feet is a hull. The hatch opens outward into vacuum. Houston is a radio call away, but the radio call takes 2.6 seconds to complete a round trip. And in the time it takes to complete that round trip, the system state may have changed in ways that make the question you just asked obsolete. You are operating in real time in a universe that does not pause. Victor Glover, who served as pilot of the Artemis II mission, had previously spent 168 days aboard the International Space Station as part of the Crew Dragon Resilience mission. He understood spaceflight not as an abstraction, but as a physical, embodied experience. As the specific weight of a pressure suit, the specific smell of recycled cabin air, the specific visual texture of the Earth seen from orbit through a porthole. He had learned, through those 168 days, what it feels like to have the planet beneath you at a distance that is large but still comprehensible, still close enough that the curvature of the atmosphere is visible, that city lights are identifiable from orbit, that the relationship between up and down retains a vestigial meaning. The translunar trajectory of Artemis II moved beyond that. It moved beyond the distance at which the Earth retains any meaningful visual reference to human scale, at the apogee of the Orion capsule's lunar flyby trajectory, at the farthest point from Earth that any human being had traveled since December 1972. The planet was a disk, a circle of blue and white and brown hanging in blackness, small enough to be covered by an outstretched thumb. Every human being who has ever lived, with the exception of the 24 Apollo astronauts, had spent their entire existence on the surface of that disk. Every city, every ocean, every mountain range, every war and scientific discovery and cultural achievement, all of it contained within the geometry of that small, bright circle. From that distance, it is impossible to maintain the ordinary human illusion that the universe is organized around human concerns. The cognitive shift that occurs when a human being sees the Earth from deep space is not merely emotional. It is epistemic. It changes the structure of what you know, not just what you feel. The overview effect, the term coined by writer Frank White to describe the perceptual transformation reported by astronauts who view the Earth from space, is not a metaphor or a philosophical posture. It is a genuine alteration in the neural representation of scale, of context, of the relationship between the individual and the cosmos. The Artemis II crew experienced this while simultaneously managing a thermal anomaly that was testing the limits of their vehicle's fault management architecture. The juxtaposition is staggering in its philosophical density. On one level, they were 4 human beings performing technical procedures in response to an engineering problem, consulting checklists, monitoring telemetry, communicating with flight controllers, executing prescribed responses with precision and discipline. On another level, they were 4 human beings suspended in the middle of a cosmic void, looking back at the entirety of known human civilization compressed into a disk smaller than their thumbnail. While the laws of thermodynamics pressed against the boundaries of the systems keeping them alive, both of these things were simultaneously completely true, and the ability to hold both of them, to function as an engineer while existing as a cosmic witness, is perhaps the defining psychological achievement of human spaceflight. Christina Koch, who served as mission specialist on Artemis II, held the record for the longest single spaceflight by a woman. 328 consecutive days aboard the International Space Station, completed in 2020. In the years of interviews and reflections that followed that mission, she spoke with consistent eloquence about the specific quality of the perspective that long-duration spaceflight produces. Not the dramatic, overwhelming revelation of the first orbital sunrise, but the quieter, deeper transformation that occurs after weeks and months of living in orbit, of watching the planet rotate beneath you, of internalizing the rhythms of a universe that operates on timescales and at scales that dwarf everything human. She brought that perspective to Artemis II. And in the context of the thermal anomaly, in the context of an unplanned scenario developing in a vehicle moving deeper into space than any crewed mission in a half-century, that perspective was not a distraction. It was a resource. Because the ability to hold your situation in cosmic context, to maintain a kind of philosophical equanimity in the face of genuine danger, is not separate from technical competence in high-stakes environments. It is part of it. The crew member who can simultaneously perform a precise technical procedure and maintain awareness of the larger situation, who can zoom in to the detail and zoom out to the context without losing either, is the crew member whose judgment can be trusted when the situation moves outside the boundaries of the checklist. And the situation during the Artemis II's thermal anomaly was moving outside the boundaries of the checklist. Jeremy Hansen, the Canadian Space Agency astronaut serving as mission specialist alongside Koch, was on his first spaceflight. He had trained for years. He had prepared for this mission with the exhaustive, comprehensive dedication that the selection and training pipeline demands. But there is a specific quality of knowledge that only the experience of actual spaceflight can produce. A calibration of intuition, a ground truth for the simulations that no amount of preparation can fully substitute. Hansen was acquiring that knowledge in real time, in a vehicle experiencing an anomaly at a distance from Earth that no Canadian had ever reached. The cognitive and emotional load on all 4 crew members during this period was extraordinary, not debilitating. Their training was too thorough for that, but extraordinary, because they were being asked to perform simultaneously at the peak of their technical expertise while existing at the literal frontier of human experience. While the thermal margins were shrinking and the fault management system was making automated decisions, and Houston was providing analysis across a communication gap that felt, in those moments, vast in a way that the numerical 2.6 seconds does not capture. Because distance in space is not just a geometric quantity, it is an experiential one. The 200,000 kilometers between the Orion capsule and the Earth at the time of the anomaly was not merely a number. It was a lived reality. The specific texture of isolation that comes from knowing that no rescue is possible, that no additional resources can reach you, that whatever happens next happens here in this capsule, with these systems, with these 4 people, and no one else. Every previous human spaceflight mission had operated with this knowledge in the background. Apollo 13 made it foreground, made it the central, defining drama of crewed spaceflight's most celebrated survival story. But Apollo 13 occurred at a moment when the space program was young, when the margins were understood less precisely, when the engineering was in some ways cruder and in other ways more accepting of improvisation. The Artemis II mission occurred in an era of extraordinary technical sophistication. Its systems were designed with layers of redundancy and fault tolerance that would have seemed almost impossibly advanced to the engineers of the Apollo era. Its crew was trained to standards that Apollo-era mission planners could scarcely have imagined. Its ground support infrastructure was vastly more capable, its telemetry more detailed, its real-time analysis more powerful. And yet, the thermal anomaly developed anyway. Because sophistication does not eliminate the gap between the model and the territory. It narrows it enormously and at great cost. But it does not close it. The gap between what can be anticipated and what the universe actually delivers is not a function of engineering skill. It is a function of the nature of complex systems operating in environments that are never fully known. This is the lesson that every major spaceflight incident teaches, and that every generation of space engineers must relearn in some form. Not because previous generations failed to communicate it clearly. They did. The lesson is encoded in every safety review, every failure modes analysis, every design review board that has ever convened. The lesson is known. It is simply that knowledge alone does not close the gap. The gap can only be narrowed through the accumulation of real missions, producing real data about the real behavior of real hardware in the real environment of space. And Artemis II was producing that data in real time, in the most direct and consequential way possible, through a live anomaly aboard a crewed vehicle at the edge of the distance envelope of human spaceflight. The question that was being answered in those compressed seconds of thermal margin consumption and automated system response and crew procedure execution and ground analysis, the question that the universe was posing to the machine and the people inside it, was not merely a technical question. It was the oldest question in the human relationship with the unknown. Are you ready for this? A cascade failure does not begin with a catastrophe. It begins with a number, a single measurement, on a single sensor, reading slightly outside its expected range. It is quiet. It is almost invisible in the flood of telemetry data streaming from a spacecraft. Thousands of data points per second, each one a snapshot of some physical parameters somewhere in the vehicle. Each one compared in real time against its nominal range by automated monitoring software that has been programmed to notice the difference between acceptable and concerning. The number that began the Artemis II cascade was a temperature reading. A temperature reading on a component that was not supposed to be the focus of anyone's attention during the translunar coast phase. It was not a dramatic number. It was not a number that announced itself with alarm tones and flashing caution lights. It was a number that crossed a threshold. A software-defined boundary that existed precisely because engineers had thought carefully about what it would mean if that particular measurement reached that particular value. It meant that the thermal margin on that component had been reduced to a level that required a response. And the response, automated, immediate, technically correct, initiated a sequence. To understand a cascade, you need to understand the concept of coupling. In engineering and systems theory, coupling describes the degree to which the behavior of one component affects the behavior of another. Loosely coupled systems are robust. A failure in one component propagates slowly and weakly to others, giving the system time to absorb and compensate. Tightly coupled systems are efficient and powerful and extraordinarily vulnerable. A change in one component propagates rapidly and forcefully through the network, and the system's response to that change can outrun the ability of human operators to track and manage it. A spacecraft is one of the most tightly coupled systems human beings have ever built. It has to be. The mass constraints of spaceflight are absolute. Every kilogram launched into orbit costs thousands of dollars, and every kilogram sent beyond orbit costs more. This economic and physical reality drives spacecraft designers toward integration, toward shared resources, toward components that serve multiple functions simultaneously. The same fluid loop that cools the avionics also regulates cabin temperature. The same power distribution system that runs the life support also feeds the propulsion control electronics. The same data network that carries crew communications also carries fault management commands. This integration is elegant. It is weight efficient. It is thermodynamically intelligent. And it means that when any one thread of the integrated system is pulled, the entire fabric moves. The automated response to the initial temperature anomaly pulled a thread. It adjusted the vehicle's orientation. A small rotation, a few degrees of change in the barbecue roll rate, designed to reduce solar loading on the affected component. This rotation was physically correct. It achieved its intended effect. The temperature of the targeted component began to stabilize. But the rotation changed the angle at which the service module's radiator panels faced the void. The radiators, which had been oriented at an angle optimized for the previous thermal state, were now receiving slightly more reflected solar energy from the moon's surface. Albedo radiation, sunlight bounced off the lunar regolith at an angle that the thermal model had characterized as negligible at this phase of the trajectory, but which in the actual mission geometry was proving to be slightly more significant than the model predicted. Albedo. The word comes from the Latin for whiteness. It describes the fraction of incident light that a surface reflects rather than absorbs. The moon's albedo is approximately 0.12. It reflects about 12% of the sunlight that strikes it, absorbing the rest as heat that slowly radiates back into space. 12% sounds small. At lunar distances, with the sun's full irradiance of 1,360 watts per square meter illuminating the entire visible lunar disk, 12% represents an enormous quantity of reflected energy washing across the space between the moon and the Orion capsule. This energy was not absent from the thermal models. It was included, but its angular distribution, the precise directional pattern of the reflected radiation as a function of the capsule's position relative to the moon and the sun, was modeled using simplifications that were appropriate for nominal mission geometries. The actual geometry of the Artemis II translunar coast, combined with the specific rotation adjustment made by the fault management system, placed the vehicle in an orientation where the simplified albedo model was less accurate than the engineers had expected. The result was that the radiator panels, in their new orientation, were rejecting heat slightly less efficiently than the thermal model predicted. Not dramatically less efficiently, not catastrophically less efficiently. Slightly, by a margin that, in isolation, would have been absorbed by the system's thermal capacitance. The ability of the vehicle's mass to absorb heat gradually without immediate temperature consequences. the thermal equivalent of a savings account that can be drawn upon during temporary deficits. But the thermal capacitance account had already been partially drawn down by the initial anomaly. The system was not starting from a nominal baseline, it was starting from a slightly degraded state. A state in which the available margin was already reduced. And now a second, independent source of thermal loading was adding to the deficit. This is the geometry of a cascade. Not a single large failure, a sequence of small ones, each individually manageable, each individually within the design envelope, but occurring in rapid enough succession and with enough interdependency that their combined effect exceeds what the system was designed to handle in isolation. The fault management software detected the secondary thermal deviation. It initiated a second response. This response involved reducing the power draw of several non-critical systems to decrease internal heat generation. A logical and correct action that reduced the thermal load on the fluid loop and gave the radiators a slightly easier task. Among the systems depowered in this action was a secondary communications relay. Not the primary communications link to Earth, not the critical command and data handling functions, but a redundant relay that provided backup capacity for certain telemetry channels. The depowering of the secondary communications relay was, in itself, inconsequential. The primary link remained fully functional. The crew could still communicate with Houston. Houston could still receive full telemetry from the vehicle. The redundancy architecture was performing exactly as designed, absorbing the loss of a secondary component without any impact on primary mission functions. But the loss of that telemetry channel meant that certain specific sensor readings from temperature sensors located in a section of the service module's fluid loop that was fed by the secondary channel, temporarily dropped out of the ground's real-time data stream. Houston could still see the primary thermal data, but the granular, high-resolution temperature map of that specific section of the fluid loop went dark for the ground controllers at precisely the moment when it was most relevant. The crew still had access to the raw sensor data through their onboard displays, but the ground's ability to perform independent, parallel analysis of the thermal state of that section of the vehicle was reduced. The collaborative problem-solving architecture, the model in which the crew handles immediate vehicle management while the ground provides deeper analytical support, was operating with a reduced information set on the ground side at a critical moment. And it was in this window, this specific combination of reduced radiator efficiency, partially depleted thermal capacitance, and temporarily degraded ground telemetry, that the third element of the cascade emerged. The Environmental Control and Life Support System, the ECLSS, the architecture of equipment and software that maintains the cabin atmosphere at the precise chemical composition and pressure and temperature that human biology requires, is thermally active. It generates heat as a byproduct of its operation. The carbon dioxide removal system